Our next session features Yashvanth Kondi, who is the principal scientist at Silence Laboratories. Yashwanth's work focuses on building secure, user-friendly cryptographic systems that bring privacy and authentication into real-world applications. He'll be sharing new perspectives on applied cryptography and its integration into decentralized systems. Please welcome Yashwanth Kondi.
Okay, yeah, thanks for that nice introduction. Okay, so today I'll be talking about decentralized open finance via secure multi-party computation, or MPC. Okay, so in this talk, I'll begin with an introduction to open finance and the account aggregator framework specifically as a concrete example, because that'll help uh, walk through things in a more like technical specific way. I'm going to then identify some gaps in such frameworks, specifically in the trust model and the incentives that the parties in these frameworks have. I'm going to propose a solution based on multi-party computation, or MPC, which I claim does mitigate some of the data duplication concerns that arise in these settings, and it should facilitate some fair compensation models to balance some of these gaps and incentives that we've identified. And also talk about a pilot deployment that we have for a particular use case in the cross-border lending scenario. That's a collaboration with Proxterra. Okay, so to begin with, what is open finance? Basically, open finance frameworks enable people or enterprises to securely mobilize their financial data from the data custodians to data fiduciaries to avail of financial services. So this could include applications like proving your financial health if you're applying for a loan, or maybe applying for an apartment to rent or something like this, or even looking for more complicated things like trade financing. So the idea behind such frameworks is to replace existing in-person protocols that involve physical documents and other such unverifiable things with cryptographic protocols that come with rigorous mathematical guarantees. And the account aggregator, or AA ecosystem in India, is one such example, and it's helpful to zoom into AA to talk about what the different actors are and what they do and so on. So in the AA framework, or in the AA ecosystem, users basically consolidate their financial information across multiple regulated financial information providers, or FIPs. You can think of these like banks. And on the user providing consent, an AA can share a curated view of the user's finances to licensed third parties, licensed financial information users, or FIUs. And then with this information, the FIUs are able to provide services to the user and like validate their financial health and so forth. So according to Samati, which is the collective that sets a lot of standards and so forth for the AA ecosystem, as of 2024, there were over 80 million users, 150 FIPs, 475 FIUs. So it is quite an active and vibrant ecosystem. But we claim that there are some issues that still persist in terms of gaps and incentives, and particularly there's a single point of failure problem that we identify. So these are the actors involved. There's a financial information provider, or FIP, a user, or a data principal, and a financial information user, or FIU. And where they sit in the ecosystem is something like this. There's an account aggregator that sort of coordinates all of their actions. First, the workflow begins with the user consenting to share data, following which there's a request from the FIU formally that is accompanied by a public key, for which the corresponding secret key sits with the FIU. The account aggregator collects these things and then forwards the request to the FIP, which then retrieves the appropriate data and encrypts it under the public key that it got through this channel, and then sends an encrypted response to the FIU. And on receiving this encrypted response, the FIU is able to decrypt and perform whatever computation it wants on this data, and then output the result of this computation and then take action appropriately. Right, so if we zoom out a bit and think about what goes into the system, like who puts in what information and gets what, we see that the FIP puts in its data D. Sorry, the FIP provides the user data D. The user provides consent to move this data, and the account aggregator gives a sort of encrypted pipeline from user consent to data being provided. And the FIU provides whatever financial service there was on offer. And what they get in exchange is dependent on who they are. So the FIU is compensated based on the business model, let's say through fees or something like this. The account aggregator typically gets paid by the FIU. And the user device the user had some reason to initiate this process, let's say like applying for a loan or something like this, so that they're able to obtain services in response. And we can already see that there's a gap in this sort of map of like who provides what and gets what in return, and that the FIP doesn't really get anything at the end. So more pressing than this is the fact that the FIU gets to see the clear text data D and operate on it. And this can be a concern if the FIU is either compromised or is vulnerable to some sort of denial of service attack. Sorry, is susceptible to some sort of insider attack or something like this, because now the data can be reused for unconsented purposes arbitrarily and without detection. Right? And this has ripple effects throughout the ecosystem, because the account aggregator now has losses in terms of fees. The user is now not able to enforce their consent on how their data is used. And as for the FIP, this is also data theft on their side, because this is proprietary data that the FIPs control, and it's not a good situation that their proprietary data sets get leaked. Right. So on a macro level, FIPs are affected as well because it is loss of proprietary data. So there are already heuristic solutions in place for this. In particular, we are aware of FIPs kind of throttling response rates in the ecosystem. This has the effect of undermining the ecosystem, and it's still not a good solution at the end of the day, because it does still leak user data, just at a slower rate and without any formal guarantees necessarily. So what we propose is a sort of compliance by design approach to solving this problem. That is, we want to make sure that the protocols that are executed by themselves prevent such scenarios. Right? And this is where we bring in secure multi-party computation as a tool to solve this problem. At a high level, MPC allows for the following situation. Each of these different nodes all hold some sort of private input, right? And they want to compute some function f on their joint inputs without really revealing their inputs to each other. Right? So how they do this is that they follow some protocol by which they generate some messages, exchange these messages, and at the end, the output of the computation drops out. But for the sake of our talk, because we don't want to be bogged down by these concrete details, we're going to assume a sort of abstraction where there's some sort of ideal box, F, to which all of these parties provide their inputs in a secure fashion. And the box, without revealing any of the intermediate states of the computation, is able to produce the output. So if we look at our account aggregator workflow again to see where exactly such an MPC might sit to solve things, it's at the FIU endpoint. So if you remember, the FIU is a single point of failure because data is exposed in the clear to the FIU. And now we can have the FIU, it generates these steps, it executes these steps, it begins with key generation to obtain data, then it decrypts the ciphertext it gets in response, and then evaluates the function on this data. Rather than doing these steps, in a manner that requires raw data, it can instead do this in a decentralized way, that is distributed versions of all of these steps. In particular, we can now replace the single FIU with a network of decentralized network of nodes that we call financial information compute units, or FICUs, that can represent different parties' interests. So now each of these FICUs operates on a fragment of the data that is mathematically guaranteed not to leak anything about the original raw data by itself, like in isolation. So assuming that the FICUs don't collude, the data stays hidden, even though they're able to operate on it and derive whatever inferences and so forth that they would like. And this is the solution that we propose. Right, so it is important that these FICUs are operated by entities that have some sort of natural incentive not to collude. Right, one configuration that we propose is that one of the nodes is operated by the FIU that's interested in the utility of the data. Another FICU could be operated by the FIP or some entity that represents the interest of the FIP, so it doesn't want the data to be leaked. And another node can be operated by the infrastructure provider that is interested in the credibility of the ecosystem. So it wants to avoid having parties take like heuristic solutions to this. So it wants to avoid things like what happens now, which is like rate limiting and so on, that doesn't have any scientific basis. Right, so this achieves protection against duplication, assuming that the non-collusion assumptions are satisfied. Right, because now that the data is secret shared rather than available in raw form, it can't be accessed by any node individually. And the MPC allows us to retain utility of this data, and that the MPC allows us to get inferences out of the data without actually exposing it to any one party. And we claim that this also does allow, it opens up an avenue to fix participation incentives, because now through the MPC, we can track when the data is being used and how, right? And this, we hope, does give a pathway to like this notoriously hard problem of quantifying how valuable data is, right? So the FIP, if you remember, wasn't getting any value out of the system. Now we can at least assign some notion of value to the data that it's providing and hopefully compensate the FIPs accordingly. Right, so on a technical level, what we propose and what we implement through our library and so on is an MPC where there are 3 parties, and we assume that there's no colluding pairs. So you can think of this as the honest majority setting. And we also protect against any active protocol deviations by these parties. So the ideal functionality, or the sort of abstract box that these parties realize, is the following. They first sample a key pair, like a secret key and a public key, and provide this public key to the AA ecosystem so that it's able to get back encrypted data in this form. And then upon receiving this encrypted data, it decrypts the data and then processes it as per the business logic. And the third step, that is getting the data from the ecosystem and then decrypting and parsing it. This is the step that is somewhat technically involved, in that it entails some operations that change as per the specifications of the ecosystem. And so the other steps, like that's key generation and like business logic and so forth, these are generally well-studied problems, and we can draw on standard techniques for these things. But the sort of integration gadget that's just decrypting and parsing data ends up being like a fairly deep problem that we have to solve on a case-by-case basis. So the guiding principle that we follow, like for example, in the AA case, is that we assume that the protocol specifications are set outside of the control of the MPC. Right? So we design our MPC protocols in a way that you can plug into these ecosystems right away, as opposed to having to wait for standards to be more MPC friendly or something. And concretely, the two aspects of integration with these ecosystems that ends up being challenging are first decrypting the data and then parsing the data after it's been decrypted. Right? So to say a little bit more about that, if you abstractly think of decentralized decryption as a way of putting a ciphertext into a box and then running some sort of algorithm that produces shared outputs, like secret shared outputs, there are bespoke ways of realizing this box. There are bespoke MPC protocols that can instantiate this sort of functionality, but actually being compatible with standards that people use in practice and things like the AA ecosystem uses, like this is somewhat challenging. At a high level, the fairly standard format for encryption that you would see is doing some sort of exponentiation with the public key and then hashing the result to derive some sort of key and then using this key to key AES, right? And for starters, the fact that each of these computations have different efficient native representations already gives us some problems. Like AES and SHA are usually best represented as Boolean circuits, but then these public key operations have a different format of native representation. And if you've sort of seen work on doing like oblivious TLS, like doing TLS inside of MPC, the problems are quite similar, and we can borrow some techniques from there. The high level, we basically go through an intermediate representation where we do arithmetic MPC that has efficient ways of converting back and forth from each of these endpoints. Yeah, so that can be handled. The next step is, after you've decrypted the data, you have to parse it, and this turns out to be quite challenging. And this may not be intuitive, and this, in fact, was not intuitive to us when we started the project, and we realized that this is a pretty non-trivial thing. So the challenge is as follows. So with like what are we parsing, right? The data that we're parsing in MPC are basically like bank statements, right? So bank statements you can think of as consisting of like transactions in some sort of format, let's say XML. Each of the entries in this file follow this sort of format. Like there's a transaction, I mean, there's the name of the field, then there's some sort of identifier, maybe an amount, and then some other narration and so forth, right? How would you parse this in plain text? Basically, you would isolate the delimiters and then like read this into some sort of structure, let's say. But now, if you're operating over secret shares, that is, you're operating over encrypted data, you don't actually know where all the delimiters are, right? The first step maybe could be just identifying where the delimiters are, right? Like we know that this is a transaction, we know that it's going to have delimiters. Let's just expose these things. Like let's just expose the locations. And it turns out that this already like runs into some problems because just seeing the length of each field does leak information. So in this case, for example, the length of the amount field leaks the order of magnitude of the concrete value inside, right? So like seeing that the amount field is 10 characters long versus 11 characters tells me that it's less than 100, let's say. Like the value of the amount is less than 100. Right, so how would we actually solve this? Our approach is something like this. So the ideal situation would be if revealing the delimiters didn't cause any problems, right? That if we had some sort of fixed length for each field, and we basically develop a protocol that lets us get to this ideal stage, right? So the task is something like this. We have each of these entries, like this is what we actually have. But what we would like is to reach a stage where each of these fields has some maximum predefined row length, so let's say 10 characters. And all of the spaces between the actual payload value of the data and the like maximum row length is padded by some predefined padding character, in this case represented by some sort of hash. The protocol that we use to actually achieve this is somewhat technically involved. I mean, I'm happy to talk about it if there's interest later on, but I will skip that in the interest of time. Right, so in terms of practicalities, we did run a pilot deployment with some partners. We ran it with an account aggregator, a financial information user, and a technology service provider. And the high-level takeaway for now is that this still needs some work in terms of fine-tuning the economics of the model, which is going on. And this model does generalize, right? So as was alluded to earlier, we ran this pilot with Proxterra. We are running this pilot with Proxterra, which is this like cross-border financing scenario where there are lenders in Singapore who want to finance MSMEs looking for loans in Ghana. And the issue is that the checks that these lenders want to perform, it has to be done on data that cannot physically leave Ghana. So how do we do this? We adopt this FICU paradigm again. So we configure the system in such a way that there is no information that actually leaves like the borders of Ghana physically, right? There are 3 nodes, like 3 FICUs, 1 in Singapore, 2 in Ghana. And the nodes are run by technology service providers, right? So they run a sort of distributed protocol once they've pulled data from the FIPs. And upon running this protocol on this secret data, they're able to run whatever checks they need to validate that this is a creditworthy person or a creditworthy institution or MSME before granting the loan. And all of this is done without actually moving the data physically out of the borders of Ghana. And yeah, this is a pilot that we have ongoing with Proxterra. Right, so in conclusion, open finance frameworks are increasingly popular worldwide, and one concrete example is India's account aggregator framework. And we propose the FICU paradigm as a way of decentralizing certain aspects, particularly the FIU in such frameworks, like the data fiduciaries in such frameworks, which we make the case does close some gaps in incentives and trust. And one of the big problems that it solves is this problem of undetected duplication on the data fiduciary side. So we have a white paper that I'd invite you to read, the QR code. And for the cross-border lending the cross-border lending scenario that I mentioned in the last slide, we have this short video that we prepared for the G20 submission, this G20 tech sprint submission, which I think does give a nice overview of how this application works, made by my colleague, Kush. Okay, with that, I'm happy to take questions. Thanks.